Hi, welcome to our final presentation for our CS225 final project. My name's Ayush.
My name's Ethan.
My name's Nitya.
Unfortunately, Nathan couldn't be here. He's in the hospital right now, but he did contribute to the final project to the same amount as we did. So the leading question that we were hoping to answer was sort of designing a cheat code to the web game Wikispeedia, wherein we find the shortest path between any two given Wikipedia articles using three different algorithms, which was the breadth first search, Dijkstra's algorithm, and IDDFS. And then once they're done running, we'll compare the runtimes. We were able to successfully implement all three algorithms within the efficiency and space constraints that we initially specified.
So for algorithms, we use the following algorithms to find the most efficient path from a chosen source Wikipedia article to a chosen destination Wikipedia article. We use breadth first search, Dijkstra's algorithm, and iterative deepening depth first search, which is abbreviated to IDDFS. And the goal of our project was to compare these algorithms by runtime to determine which of them was the most efficient for finding the shortest and most efficient path.
So our first step that we had to think about in order to get this project going was how we were going to parse the data. We got our data from the Snap dataset, which involved having TSVs filled with both the article names and then articles and their corresponding links. And the first issue we came across was designing the graph and how we wanted to implement each individual article. And from this, we came up with the idea of a WikiNode, which would represent an article and all of its links. And then additionally, we wanted to think about how we were going to access random pages in constant time. And we came up with using a map for this, going from using the article name as a string for the key and the actual WikiNode as the value. Gathering the data from the actual TSV files is done in create graph from file. And this involved using calculating where the tab was in each individual line in order to separate the article name from its linked article. And then additionally, we went in and created progress bars to make it look a little bit nicer. A couple issues that we encountered was one, string comparison for different OSs, operating systems. We found that depending on whether or not this was run on Windows versus Mac, you could come with an issue where string comparisons would or would not include new line characters. And so to combat this and fix it, we added a check to make sure that names did not include new line characters and thus would work on either operating system. Additionally, when it came to implementing custom data sets, we discovered a few issues with designing the graph, and we had to restructure it so that we could use variables for the number of articles and links, as well as modifying get random page so that it would work with any size data set. The first algorithm we implemented was breadth first search, arguably the easiest or most naive of these three. It served as a good starting point and baseline. The general way it works is that you start at the starting node and perform a level order traversal using a queue to keep track of neighbors, similar to what we've done in class before. Additionally, we will keep a track of the parents of the nodes added to the queue. And then once you reach the end node, we use this map to trace the path backwards. Additionally, we were able to use this map that we maintain to act as a visited check rather than having a separate map for that. If the node has a value in the map, then that means we visited it and have already added it to the map. However, if that value is null or if it's at the end of the map, then it hasn't been visited. And so that serves as a really easy way to perform that check.
The second algorithm that we implemented is called Dijkstra's algorithm. Dijkstra's is a popular algorithm for finding the shortest paths in a weighted directed graph. And the algorithm works by starting at a source node in the graph and by exploring all of its neighbors and then adding the lowest cost node to the path. It's similar to BFS, which constructs a path using a first in and first out queue. Dijkstra's constructs a path using a min heap, which is a priority queue to prioritize adding nodes with shorter distances from the source of the path. In our implementation, we find the shortest path from the source article to our destination article by running Dijkstra's on the graph of WikiNodes. We use the min heap implemented with C++ priority queue, and weights are assigned to nodes based on how many outgoing links they have, which is an indicator, a rough estimate of the page size and thereby the load time of each article.
The third algorithm that we used for our purposes was the IDDFS algorithm. So it's basically a combination of both the depth first algorithm, the depth first search algorithm, and the BFS. It combines the space efficiency of DFS with the time efficiency of BFS. So here we perform the depth first search algorithm for a control depth and then recursively call the DFS function for incremented depth till you either find the end node wherein you just return the path, or you reach a maximum depth where you return an empty vector. The smart design choice that we made while implementing this was to keep a track of the visited nodes, which, although slower than the normal IDDFS, allows us to avoid cycles in our graph.
So putting it all together in main.cpp, we created a function called compareAlgs that would serve as an easy way to compare all of our algorithms in terms of path length, what nodes were actually visited as part of the path, as well as the runtimes for each of them. And so this is done using the chrono library and just simply having a start and end time before and after each function is called, and then returning that as a vector with the paths included. From there, we created a terminal visualization as a table that would display the algorithm name, length, runtime, and actual path, as was seen earlier on when we talked about our algorithms. However, there was again an issue involving custom data sets, and so we decided to enable that by modifying main to accept arguments, 4 in total, with a file path to the TSV for the articles, 1 for the links, as well as the number of articles and number of links. And from there, we were able to implement both the default data set and any custom ones that you might want to use.
So to conclude our project, we used the snap dataset of Wikipedia articles and their linked articles to find the shortest path between 2 given nodes. We used BFS, Dijkstra's, and IDDFS algorithms to discover an efficient path from the source node to the destination node. And the surprising discovery that we made was that IDDFS was by far the fastest algorithm to find the most efficient path due to its optimization of time and space complexity. And we also discovered that the occurrence of a path not found between source and destination Wikipedia article was more common than we anticipated, meaning that Wikipedia is not as well linked as we previously thought it to be.